So this is the main reason why radioactivity is so useful and so prevalent. Um, it can be detected. So it's used in therapy, medical therapy, it's used in archaeology, it's used in research and industry. So again, it's because it can be detected. So there's two types of detection, um, ways of detecting. One is an ionization counter and one is a scintillation counter. They're just used to count particles emitted. Um, this picture here is a Geiger counter, which is a type of ionization counter. Basically, the radioactive nuclei goes into the tube, and there's argon gas, and it causes charged particles to be produced, and which are detected. Not critical that you understand the the system behind it. And then another type of detection is called a scintillation counter. Um, in this one, it can detect things that are really pretty small samples, because what happens, you can see this, the radiation goes into the chamber, and then it gets multiplied. It hits these different sides, and every time it hits, it'll multiply the number of electrons or photons, and then you get a pretty good signal. All right, so just a few little things that are not critical, but is helpful to know. So the activity of a radioactive source is the number of nuclear disintegrations per unit time. So one of the units that we use to measure radioactivity is called a Curie, and this is a unit of activity equal to 3.7 times 10 to the 10th disintegrations per second, or DPS. So if you have a sample of technetium that has an activity of 1 times 10 to the minus 2 Curie, then you can multiply them, and you find out that there are 3.7 times 10 to the eighth nuclei per second decaying. So it's just a measure. It's kind of a measure of concentration. It's not going to be critical for you to remember this unit. To monitor nuclear radiation in biological tissue, it's also necessary to measure the radiation dosage. And so we have a couple of other units. The RAD, which stands for radiation absorbed dose, is the dosage of radiation that deposits. You can read this: 1 times 10 to the minus 2 joules, or 0.01 joules of energy per kilogram of tissue. Again, it's not critical that you remember these definitions. I'm just introducing them to you. Now, it's important to remember that the biological effect of radiation depends not only on the energy, but also on the type of radiation. So there is another unit called the the REM, which is a unit of radiation where the rads are multiplied by some kind of a factor called an RBE factor, or relative biological effectiveness factor, which depends on the type of radiation involved. So if it's beta or gamma radiation, the RBE is about 1. So rads and REMs and rads are about the same. But a neutron radiation is about 5 times as bad. So the REMs are about 5 times the rads. And alpha radiation actually has an RBE of 10, so it's even more, has a much larger effect. And just note, a single dose of about 500 REMs is fatal to most people. So the effect of radiation on human health will be determined both on the type of radiation and the amount of radiation. Now, unless you work at a nuclear plant where there's the danger of a nuclear meltdown or something like that, the greatest danger to living organisms of exposure is to long-term low-level radiation. Now, the reason why, so that's like background radiation. This long-term, low-level radiation has the ability to dislodge electrons from molecules, and they generate something called a free radical. Free radicals, so they're missing an electron, which means they're very, very reactive. They're going to react, bombard anything that comes along. So cells, genes, chromosomes, whatever, it's going to do a lot of destruction. So it can lead to genetic mutation, can lead to cancer or other serious conditions. The free radicals, you've probably heard of antioxidants. We take antioxidants, which are vitamins that have a lot of extra electrons that are not as needed, and so those the antioxidants can often quench the free radicals and keep them from doing damage. But so we have so we have the long-term low-level radiation, but we can also, if you have short-term exposure to intense radiation, of course, it's going to result in tissue destruction of the exposed area and cause symptoms of acute radiation syndrome. So that would be, mainly we think of nuclear meltdown kind of thing in acute radiation syndrome. But also, if someone's getting radiation treatment, probably that very small area where they're limiting the radiation to can be burned or can have dead skin, things like that. So there are definitely health effects from radiation. So how can you protect yourself from radiation? Well, a couple of the most common things is, well, first of all, distance. The farther away you are, the less likelihood of getting infected or affected by the radiation. And then the other thing is to use some kind of shielding, which prevents exposure. So you've probably all been to the dentist, and if you've had x-rays, which x-rays are not radiation, but they are high energy, and they can do a lot of the same kind of destructiveness to health, to body. It's the same as radiation, and so the similarities are there. But you have, what did they do? They usually put a big heavy lead shield in front of you when they're taking x-rays, and then the technician or the dentist or whoever goes out of the room. So they're also putting into practice distance. So they're moving away. Anyway, shielding, as you can imagine, involves the placement of a dense absorbing material such as lead or concrete between the radiation source and the individual. But what material stops certain radiation differs depending on the radiation, because every kind of radiation has a different type of energy related to it. So for example, alpha particles are the heaviest, and so they move the slowest, so they really kind of have the lowest energy, and can be stopped easily just by paper, skin, clothing. They only travel a few centimeters before they collide with air molecules and lose their radiation or energy. So, however, if you ingest or inhale alpha particles, they actually have that much higher RBE factor, and so they can actually do a lot of damage. Beta and positron particles are very small in mass, so they move much faster and much farther. They can travel as many as several meters before being stopped. They can move straight through paper and several millimeters into a body. And so you have to have very heavy clothing or it doesn't need to be real thick lead, but some kind of lead will stop beta particles. Gamma and neutron radiation, gamma doesn't even have mass. They travel very far, very fast. They can go through many types of material. And so only dense shielding such as lead or concrete will stop this kind of energy. So this is just a picture showing alpha can be stopped by skin, beta can go straight through a body but can be stopped by some aluminum, maybe some lead. Gamma rays can be stopped by lead, and x-rays as well. and the neutrons need very, very thick concrete. There's a little video here that you can watch that sort of demonstrates this, where they have different types of radiation, alpha first, and then beta, and then neutron radiation. And so they they sort of put something there in between the radiation and the Geiger counter so that you can see what's actually stopping the radiation. So now we're going to move into rate of decay. So all radiation does disintegrate, but they don't all disintegrate at the same time. So the rate of radioactive decay, which is the number of disintegrations per unit time, is proportional to the number of radioactive nuclei in the sample. So it actually follows first order rate law. Rate equals K times NT, where NT is the number of radioactive nuclei at time T, and K is the decay constant. So this is just first order rate law. Rate is related to the concentration to the first power. So it's all first order kinetics, and you might go back and review that from chapter 14. So first order kinetics, you can measure a half-life, which we know the half-life is the amount of time required for 1/2 of the concentration to be reacted, or in this case, because it's radioactive, to decay. So after one half-life, half of the amount of nuclei will decay. So the first order relationship between the half-life is, we've seen this back from first order kinetics, T1/2 equals 0.693 over K. So if you put half of the concentration in, you get the half-life, and take the natural log of 1/2 is 0.693. And so this is the relationship between K and T1/2. So let's just do a quick example. The decay constant for the beta decay of technetium is 1 × 10⁻13 inverse seconds. What is the half-life of this isotope in years? So first, we know that T1/2 is 0.693 divided by 1 × 10⁻13 inverse seconds. So that gives you 6.9 × 10 to the 12th seconds. That's how long the half-life is in seconds. This question asks for it in years, and so you just have to convert from seconds to years. And I did that to point out to you that you always want to make sure that your half-life and your K value are in the same units, or you have to convert them. So 6.9 × 10 to the 12th seconds, you could divide by 60 seconds, 60 minutes in an hour, 24 hours in a day, 365 days in a year. And so the half-life of this isotope is 2.2 × 10 to the 5th years. So that's still pretty long. All right, so now once you know the decay constant, which you can find from the half-life or vice versa, now you can calculate the fraction of radioactive nuclei remaining after a given period of time. And again, this is just like first order kinetics. So first order kinetics says that the natural log of the concentration at time t over the concentration at time 0, the initial concentration, equals minus kT. So T is the time and NT is the concentration at that time. So again, it's just first order integrated rate law. The only thing that might be a little different is just the way that the concentration is expressed. In chapter 14, we usually use brackets indicating molar concentration. Well, this is going to be in different units, like disintegrations per minute or disintegrations per hour or whatever, or some other unit. But the key thing is that it's just a type of concentration, and you can use this equation. All right, so let's look at an example. Gallium-67 is used as a tumor-seeking agent. Its half-life is 78.2 hours. What fraction of the sample will remain after 260 hours? So our time, T, is 260 hours. and we're just looking for the ratio, so we don't know what the initial concentration is or the final, but all we want is the ratio. Now we do know the half-life, and so we can find K. So K, we know K is just equal to 0.693 over T1 half. So here's our first law. First of all, we substituted, in place of K, we just substituted 0.693 divided by T1 half. So they just substituted that straight into this equation. And then if we end up finding NT over NO, we'll have found the fraction of sample remaining. So the amount at time T divided by the initial amount is the fraction remaining. Okay, so if we plug T in, 260 hours, we plug T1 half in, which is 78.2 hours, into this equation. Make sure that they're the same units. So the natural log of NT over NO equals negative 0.693 times time, 260 hours, divided by the half-life, 78.2, gives us negative 2.304. Then if we do the inverse natural log, which is E, we undo the natural log, we get the ratio NT over N naught equals E to the negative 2.304, which is 0.1. That tells us that we have 1/10 or 10% of the original amount remains. All right, so let's talk a little bit about applications of radioactive isotopes. Radioactive isotopes, like I said earlier, they're very useful. Number one, because they react chemically just like any other isotope. So if we're talking about gallium, or if we're talking about iron in the blood, iron reacts like iron no matter what type of isotope it is. However, the radioactive isotopes now can be detected. So if your body uses iron, in your blood, but they give you radioactive iron, then they can follow it along and see where it's going, if it's doing what it's supposed to do. So the key thing is that they react chemically just as they're supposed to, however they can be detected. So here are some examples of applications for radioactive isotopes. Archaeological and geological dating, scientific research, medical diagnosis, medical therapy, and then also industrial uses. So I'll talk about each of those a little bit. So carbon dating. In certain situations, we want to know how old something is. Is that painting really 500 years old, or is it a fake reproduction? Is that that canoe, was that really built by the Indians 2,000 years ago, or was it is it a fake reproduction or whatever? So carbon dating is one way to do that. You can date historical artifacts that have some kind of carbon in it, either people or trees or anything that's organic in nature. So we know that carbon is primarily carbon-12. About almost 99% of all carbon is carbon-12. And then the other 1.1% pretty much is carbon-13. However, there are traces of carbon-14 in the atmosphere. About 1 in 10 to the 12th atoms is carbon-14. So it's a very small amount, but yet it exists. It's in atmospheric carbon dioxide, and it's in living materials, anything that has carbon in it. So carbon-14 is radioactive, and it's a beta emitter. It has a half-life of 5,730 years. And it turns out that if you have 1 gram of sample of carbon from a living sample, so it's still incorporating it, or the carbon in the atmosphere, it shows about 15 disintegrations per minute. So that's a concentration. So how does carbon dating work? Well, plants continually absorb CO2 and convert it into their organic material, whatever the plant, and this can be true. I'm just sort of using a plant like a tree for an example, but other the idea is that as long as it's living, it is incorporating CO2 into the living tissue. And as long as the plant remains alive, this process continues. And so the percent of carbon-14 in the living tissue is the same as the percentage in the atmosphere, which we said was about 15 disintegrations per minute. However, when the plant dies, the plant no longer takes up new carbon into its body, and so carbon-14 is no longer introduced. Now the carbon-12 and the carbon-13 is not radioactive, so that stays the same, but the amount of carbon-14 starts to decrease over time because it is radioactive and will start to decay. So after 5,730 years, which is the half-life, half of the carbon-14 will be around, and so the activity will be 7.5 disintegrations per minute for each gram of plant. So half, after the half-life, you'll have half the concentration. Then you can compare, so you can measure some kind of, so say you're trying to carbon date some kind of old canoe that was made out of a tree trunk. You can measure the activity of carbon-14, how many disintegrations per minute are coming off of it, and then compare it to the 15, which would be in currently living tissue. So we can compare the concentration in the material to living material to know how long it's been dead. So that gives us a pretty good idea of how old something is. So, for example, a sample of cypress wood has an average activity of about 7.04 disintegrations per minute per gram. What is the approximate age of this sample? So we're going to assume that the atmospheric carbon is 15.3 disintegrations per minute per gram. So again, it's just a concentration. So the first thing we're going to do is figure out what the rate law constant is, 0.693 divided by the half-life. So K is 1.21 times 10 to the minus 4 inverse years. And then we can just plug it in. So our concentration currently is 7.04. The initial concentration is 15.3. It equals negative K times T, and we're looking for T. So the ratio 7.04 divided by 15.3 gives us 0.460. If we take the natural log of that, we get negative 0.776. Divide both sides by 1.21 times 10 to the minus 4th negative, and we get 6,420 years. So that tree, you can sort of see 7 is a little bit more than half of 15.3, so this should be a little bit more than a half-life. So 6,420 years is how old this wood is. In a similar way, other elements are used for dating other artifacts such as rocks. So we can use potassium argon dating. Potassium-40 undergoes electron capture to produce argon-40, and so the half-life of potassium-40 is about 1 billion years. And so if you determine the percent of argon-40 in a potassium-containing mineral, we can estimate the age of the mineral. So the argon isn't there to start with, but after time, the potassium-40 undergoes this process, and if we can find out how much argon is present, then we can look at the ratios. In a similar way, we can look at uranium and lead concentrations to also date. So uranium-238 decays to lead-206 and has a half-life of 4.5 billion years. So again, the ratio So what about scientific research? So we can use radioactive isotopes in scientific research. a lot of times, again, the main thing is that the chemical reacts just like you expect it to react. However, now you can detect it, you can trace it, you can follow it, find out what's happening. So, for example, in the 1950s, the mechanism of photosynthesis was discovered again by, I'm not sure exactly, but probably by using some radioactive oxygen as a marker. So they were able to trace, does this oxygen stick with this carbon, or does it move? What actually reacts with what? Again, the chemical stays the same, but they can introduce it and detect where it is and follow the process. Did that radioactivity go out with the water, or is it still attached to the carbon, or whatever? So they were able to find the mechanism. In a similar type of scientific study, they were able to determine what the human blood volume was by introducing isotopic tracers, probably some kind of iron or something like that. All right, now we know that radioisotopes are used often in the medical field, and it can be used two ways. First, as medical diagnosis. So, for example, if you have a radioactive atom, it's going to react chemically the same way in the body as a non-radioactive atom, but you can trace it. So, for example, iodine 123 is given to a patient, and iodine's often used in the thyroid. It's the one place that iodine is used in your body, and so if you're given radioactive iodine, it can be detected. And so, for example, is your body using iodine the way it should? Does the iodine end up in your thyroid where it's supposed to, or is there a blockage somewhere? So sometimes you hear the term hotspot. So they're able to find, where is the radioactive isotope ending up? Is it where it should be or not? So this is a way of diagnosing a problem medically. Notice that it says that iodine 123 is often used for diagnosis because it gives off gamma rays. Gamma rays are easily measured outside of the body, and so that's a very good type. Therapy is a different way of using radiation. And we know that that's often used for the treatment of cancer. Why is it used for cancer? It's because radioactivity often has the most effect on rapidly dividing cells. So cancer cells are rapidly dividing cells. They're more adversely affected by radiation, and so that's why radiation is often used. And just sort of as a side note, a lot of the times, like when you get that the lead shielding, oftentimes it's really just protecting the center of your body. The other very quickly dividing cells in your body, well, blood cells are one of them, but also your eggs and sperm, the reproductive cells are also very quickly dividing, and of course they carry the genetic information to the next generation, and so that's why especially they're trying to protect those type of cells, because radiation can also do a lot of damage to reproductive cells. Anyway, gamma radiation from cobalt-60 had often been used in medical therapy to try to treat cancer. Again, the cobalt could be just, in this case, it's not going to be used so much, but directed at the cancer cells to try to kill it, because the radiation will kill those cells. Cobalt-60 isn't used anymore because it has a fairly long half-life, and so you really don't want the radioactivity to be in the body as long as it has to be. So newer radioisotopes are used, and of course it can depend on the type of cancer. I'm sure different radiations work differently on them. Anyway, alpha and beta radiation are often best used in therapy because it restricts the radiation damage to only the cancer cells and not healthy tissue. Other medical applications, these are just some examples. Technetium, and you can just read that. Technetium is used to develop the images of internal body organs. Thallium is often used to locate heart disease. Iodine 131 is is often used as treatment for thyroid cancer. Phosphorus 32 used to locate tumors. Iron 59 is used to measure the rate of formation of red blood cells. And you probably have heard of PET scan, a PET scan, which is called positron emission tomography, and that's kind of a method that again it's like a MRI where it can give you a picture of your insides, and it's because there's positron being emitted that can be detected. Industrial applications, just a few. If you're at a factory or something where they have, like maybe they're making drugs or something like that, where there's different products and they're changing over to another product, and they want to know when the new product is coming out so they can direct it a different way. What they can do is put a liquid plug of radioisotope, and so when that's detected, they know that after that is the new compound that's being, so they can move a valve and direct it to somewhere else. A very interesting application is the thickness of aluminum foil is monitored during production, and there's a radioactive source on one side of a moving strip of foil. It sends the radiation through the foil to a detector, and I guess if it's thin enough, it allows that radiation to come through. But if the aluminum foil gets too thick, it'll block the radiation or lower the intensity of the radiation, and so they'll know if there's something wacky with the thickness during the process. Another way is just that they can put radioactive in a pipe or something like that. If there's a leak somewhere, then they'll be able to detect where the leak is. So just some examples. All right, just a few other things. There's nuclear fission and nuclear fusion. So what are they? Nuclear fission is a nuclear reaction where a heavy nucleus splits into two or more lighter nuclei. And when that happens, energy is released. So an example of this, californium might break apart into barium and molybdenum, and at the same time, 4 neutrons are released. And energy. This is one of the ways where we get energy. Nuclear energy comes from is uranium. Uranium is a commonly undergoes fission. A lot of times it doesn't do it spontaneously, but has to be initiated by bombarding it with a neutron. And so if a neutron hits uranium, it might break apart into different particles. And this is fission again, because it's breaking apart into 2 or more particles. So an interesting thing, you may not be able to predict what it's going to break into. So it could break into xenon and strontium, where the 38 and 54. It could break apart into barium and krypton. It could break up into cesium and rubidium. Notice that all of these have neutrons that are also released, and so we'll see in the coming up slide that they can trigger more reactions. So more and more neutrons are released, creates the possibility of a chain reaction. So what is a chain reaction? It's a self-sustaining series of nuclear fissions caused by the absorption of neutrons released from the previous nuclear fission. In order to have a nuclear chain reaction, you have to have a critical mass. A critical mass is defined as the smallest mass of fissionable material required for a chain reaction. So just sort of as example, so here's a picture of an example. So we start the reaction off by bombarding uranium with a neutron. You can see that it goes through fission, so barium and krypton. In the process, 3 more neutrons are given off, so they may collide with other uranium. Uranium will break apart. More neutrons are released, and so you keep the process going. And so it's it's a chain reaction. So unfortunately, if you have a supercritical mass, it will decay so rapidly it will cause a nuclear explosion. Of course, if you have a nuclear bomb, then you have a supercritical mass. An atomic bomb, it turns out that what they do is they have a less than supercritical mass in separate parts of the bomb, and then it's detonated by a small chemical explosive that pushes the two masses close together. So now you end up with a supercritical mass and you will result in a nuclear explosion. Of course, hopefully within a nuclear plant, we don't reach that supercritical mass. We don't want a nuclear explosion, but there's always that threat. So here's a picture of an atomic bomb. So you've got the two orange parts, the triangle, and then the part lacking the triangle, the other part of it. Together, they're supercritical. Each of them separate are subcritical. So what happens when you're ready to ignite the bomb, you use a chemical explosive. The chemical explosive glows off. The triangle orange stuff ends up colliding with the other. Now you have a supercritical amount and we have an atomic bomb. All right, so in a power plant, the main way that we get energy is for nuclear fission. Nuclear fission has a controlled chain reaction, and then the energy is collected. The energy produces heat, which produces steam in water. So the pipes run through water, produce steam. The steam will drive an electric generator. So again, it's just a way of getting a generator to move and to produce electricity. A nuclear reactor has fuel rods that contain the material in it, and it alternates with control rods inside the vessel. And I have a picture of this coming up in just a second. A light water reactor is the most common type of nuclear reactor in the U.S. Light water just means regular water, which is H2O using the isotope hydrogen, the hydrogen-1 isotope. Sometimes we have something called heavy water, which uses deuterium in place of hydrogen. The deuterium isotope is hydrogen with a neutron in it. So that's sometimes called heavy water because it's heavier. It's got a couple more grams per mole in it because it has those extra neutrons. Anyway, so the light water reactor has these fuel rods with enriched uranium dioxide, and enriched normal uranium has the isotope uranium-235, which is the main fuel, only about 0.72% in normal uranium, and so uranium has to be enriched to make sure that we have greater than 3% of uranium-235, which is the main fuel. The way that we enrich uranium is something called isotope separation. If you're able to centrifuge it and collect the different portions that weigh different amounts, you can grab a bigger percentage that weighs 235, which is the main uranium used. Anyway, there's uranium dioxide pellets in a zirconium tube. And then the control rods have other substances that absorb neutrons easily, such as boron and cadmium. And so they can slow the chain reaction if needed. Here's a picture of a light water nuclear reactor. You can see here the fuel rods that contain the uranium, and then the control rods that are in between that can help slow down neutron absorption if it gets out of control. The heat is released into the water. The light water just means regular water. So the steam is produced. The steam comes into a steam turbine and then starts the electrical generator to get the electricity. And then the water is just recycled through again. Okay, nuclear fusion is different. And just like the word fusion means to break apart, fusion means to put together. So nuclear fusion is a reaction where light nuclei combine to give more stable heavy nuclei. But at the same time, neutrons can be released and energy is released. So again, energy is released when you break it apart, energy is released when you stick them together. An example of nuclear fusion is this reaction. So we have hydrogen with one proton and one neutron, which is called deuterium, H2. Then tritium is actually hydrogen with one proton and two neutrons. If you slam them together, you can create helium, which has two protons and two neutrons, and a neutron is also released. This fusion reaction has been observed in a laboratory using particle accelerators. So sustainable fusion requires very, very high temperature. So we obviously 100 million degrees centigrade. At these elevated temperatures, all atoms are stripped of their electrons and a plasma results. And this is believed to be where the energy of the star comes from. So this nuclear fusion of hydrogen becoming helium is where the star's energy comes from, and it gets it very hot. And so again, it continues the process. I imagine once all the hydrogen's used up, then the star will die. Also, now we talked about atomic bombs earlier, which are fission bombs where uranium is broken down, but a hydrogen bomb is a nuclear fusion bomb. The high temperatures needed are first attained by a small fission bomb that ignites the fusion reaction. That's pretty much chapter 20 for you.